Okay, I think we can start. We are very happy to have Luca Lee talking about relation between dimer model and sine-Gordon.
Yeah, exactly. Okay, so thanks for the introduction and thanks to the organizer for inviting me here. I didn't know there would be so many physicists in the audience, so I hope you will. I didn't make. So I hope you will understand what I'm talking about. If you don't hesitate to ask questions. Yeah.
You are a chemist.
No, mathematician. Yeah. Hopefully you will understand. So I'll talk about near critical dimers and the sine-Gordon field. So there will be a fermionic field theory, and the forests and trees they will be underlying, but you won't see them much in the talk. I will try to point where they are. First I will make a small introduction to the dimer model at the critical point. Then I will talk about the work we did at the near critical points. So in particular, I will present some convergence results. And then I will try to present you what's the link with the sine-Gordon model and also what is the sine-Gordon model, if you don't know. And this is based on a work in progress with Nathanaël, Berestycki, and Scott Mason, which should appear very soon on arXiv. And let me first talk to you about dimers. So the dimer model is a model of statistical mechanics. And first, I need to tell you what it is as a combinatorial object. So you start with a graph, which I take here to be bipartite. So a graph G on the left with some white and black vertices. And on the right is the extended dual graph. So it's basically the dual graph with a bit more vertices on the boundary. And a dimer configuration is something like this. So it's a way to pair together the vertices along edges in such a way that every white vertex is paired with exactly one black vertex. So this thing on the left is a dimer configuration. And there are many possible dimer configurations of a given graph. Another way to see it is as a tiling of the dual graphs. So those two things are really the same I just glue together two faces if they are linked by a dimer on the left. So those two things are really the same. And so this is just a combinatorial definition, and now we are doing statistical mechanics. So we take one at random. And how do we do that? We put a weight on the edges. So every edge has a positive weight. And then we take one dimer configuration at random with probability proportional to the product of the edge weights. So for example, in the simplest case, the weight is just one everywhere. And we are just taking one dimer configuration at random uniformly, or one tiling at random uniformly. Okay, so this is the dimer model. And there is a very nice alternative point of view on the dimer model. So now it's not the square lattice, it's the hexagonal lattice. And on the left, I have pictured the dimer configuration. And on the middle, I have the associated tiling of the dual graph. And I have put different colors on different tiles. And then you should see, a stack of cubes, right? And you can associate to every point of this stack of cube its height. And it gives you a height function like this. And actually, those three things are equivalent. So you can pair in bijection. So you can sample a dimer configuration or a stack of cubes or a height function with some conditions on the heights. Those three things are in bijection. So we are talking about the same object. And now you could, instead of sampling a dimer configuration, you can sample a height function at random with some weight. So for example, with some weight. Okay, so that's a very nice intuitive way to look at dimers. And let me give a very short history of the model. So as you, one of you said, it was introduced by chemists. So I am partly a chemist, partly doing chemistry here in 37. Then the first very interesting mathematical works on the model were done by Castellin, Temperley, and Fisher in 61, where they were able to find some determinantal formulas for some quantities and to compute many probabilities and quantities in the model. Then a very important step was the introduction by Thurston of the height function, which I have just shown you, and which led to many new interesting and geometric ideas on the model. And then there was this groundbreaking paper of Kenyon, where he obtained the scaling limit of the dimer model at the critical point. And I just stopped the history here, even though there were many things later, but because that's where I start my talk, at Kenyon's work.
I'm surprised that physicists didn't work out that height function. But of course, the almost doesn't meet.
There were results. Okay.
Yeah, but mathematicians tend to ignore.
Oh, okay. Sorry. So who should I cite? Yeah, sorry.
That's okay.
No. Okay. Okay. You'll tell me afterwards because I don't want to ignore. I mean, okay.
So maybe people like Gilhorst or like 1982 or something.
I think
like
I even went to discuss with Kenyon once.
Oh, okay.
Around these days. Don't worry.
Okay, okay. You'll tell me afterwards. So now I'll talk about Kenyon's work. Yeah, because obviously I'm not very familiar with the physical literature on the dimer model. Some things I know, but not everything. So I might miss a lot of things. I'm sorry for that. Okay, and what's this work by Kenyon, which will be very interesting for us? It is that he obtained the scaling limit of the dimer model, of the planar dimer model. So what is the scaling limit? It is the behavior of the model when the graph becomes very big. So I have a domain here, which is some open set of the plane. And this domain is approximated by some graph. Here it's a subgraph of the square lattice with a small mesh, so small edges. And when the mesh goes to 0, yes, this subgraph approximates the set. And the question is there a limit for a random dimer configuration? Does it converge towards something? So on the left, I have pictured the random dimer configuration. And well, even if the graph is big, you don't see much. What would this converge to? I don't know. But if you picture the height function, so this is not the height function associated with this. This is the height function on the hexagonal lattice because it's easier to see, but the same would happen on the square lattice. Then if you take a very large graph and you look at the height function, you see there might be some hope that this will converge towards something, towards some deterministic or random surface in the limit with some prescribed boundary condition. And this is exactly what Kenyon proved. If you take a planar domain with some particular boundary conditions, which are called Temperleyan, and if you look at the critical weights, so the critical weights are just weight 1 for every edge, then the height function converges towards some random surface, which is called the Gaussian free field. And this convergence falls in the sense of distribution. So something like this, when you integrate the height function against the test function, then it converges toward the Gaussian free field.
What are the boundary conditions?
The boundary conditions for the what? For the GFF. So here it is actually the centered height function. So I should have mentioned this. And the GFF has Dirichlet boundary condition. Okay.
What's the Temperleyan domain?
Okay.
Maybe.
Yeah, okay. I just need
point of view.
Well, it's a domain which has some particular boundary conditions. So if you look at the square lattice, and okay. Do you know temporalist bijection? Okay. Temporalist bijection is a bijection between dimers and trees and uniform spanning trees. And the Temperlian boundary conditions are those where this bijection hold. And it's something where you have the boundary of your domain. This. And then you remove one corner of the domain. And this is what is called Temperlian boundary condition. Okay. Okay. So with this boundary condition, and if you look at the centered height function, it converges towards the Gaussian free field. So the Gaussian free field is not defined pointwise. It is a rough random surface. It is defined in the sense of distributions only. And an informal definition is that the Gaussian free field is a Gaussian vector with this correlation function given by the green function, the Dirichlet green function of the domain. But you see, this is not a proper definition because on the diagonal, this explodes. So you cannot define this as this Gaussian vector, and you need to work a bit more. But this has been worked out quite some time ago, and this is the result of Kenyon. And I would just like to mention some elements of proof because we will see them later in the talk. So a very important object for the dimer model is the Castellane matrix, which is, so you have your graph, and then you put some orientation on the edges. So there is a particular way to do this, which I will not present right now. But if you choose the orientation properly, and you define the Castellane matrix as just the adjacency matrix of the graph, then you can express many quantities in the dimer model in terms of this matrix K here, so Kn. So you can express, for example, edge probabilities or the partition function of the model. This was the work of Temperley, Fisher, and Castellane, which I mentioned before. And you can also express the height function or expectation of height function in terms of this inverse Castellane matrix. So you have formulas like this. This is quite big, but so you have on the left moments of the height function at different points. And this is so the sum is over paths from boundary points to the faces where you want to compute the height function. And so the important thing is that this is the quantity which depends on the Castellane matrix and the inverse Castellane matrix. So you have a determinant involving inverse Castellane matrix. And the way Kenyon obtained his results is that he was able to compute an asymptotic of the inverse Castellane matrix in terms of derivatives of the continuous green function. And then he plugs the asymptotic in this formula and he obtains the result, basically. Okay.
Can you, so because there are paths between
I'll make
the points.
Yeah, I draw something. So you have your domain. So I put a straight boundary there. There's a reason for this, but I'll tell you later. And you want to compute the height function at some f1, f2, 3, for example. And you take some path. So from the boundary, so this is the discrete. You take some path here. Gamma 1, gamma 2, gamma 3. And then you sum over the edges of this path.
You start anywhere on the boundary?
You start anywhere on the boundaries. Okay, so is this clear for the moment? Perfect.
They
Yes.
are branches of this tree that you get by this temporary projection, or
The paths?
yes?
No, you just choose them the way you want. They are deterministic paths. Yeah, you can choose them straight if you want. You can.
Well, you have to sum over all passes or just
No,
one
just
pass?
you take
Okay.
any three paths,
Okay, sure.
and it doesn't depend on the path.
Okay.
The result does not depend on the path. Yes. Okay. Okay. So if everything is clear, I will go now to the near critical timer model. So here, the model was critical. So the weights were just 1. So if all weights are 1, the model is in his critical phase. But what we want to do is to look at the near critical dimer model. And the near critical weights are a small deformation of the critical weights. So I must start with a deformation potential V. So I have some function V, some real valued function on the domain. Its gradient alpha, I call it the deformation vector. And there is an associated mass, which is this thing, right? So no, I tell you that there is an associated mass, and we must do an hypothesis on the potential, which is that the mass here is positive. Okay, so this might not be very important for you at the moment. And what is the near critical model? Well, I have a portion of the graph here. I have a white vertex, a black vertex, and a weight on this edge. And in the critical model, this weight would be 1. In an off-critical model, for example, you would have weight 1 here, 2 here, weight 1 on every vertical edge and 2 on every horizontal edge. And the near critical model is something in between, where the weight is given by this explicit formula. And so it is, to the first order, it is 1 plus 1 over n times the scalar product of the deformation vector and the direction of the edge. So you have a, so you have a weight which depends on the direction of the edge of the,
N is the size of the lattice.
N is the mesh of the lattice,
No.
exactly. It's
Well,
this
right,
thing.
it means you have n sides.
And what?
You have n sides too.
Yeah, and square, because the,
N
exactly. Okay. So yeah, you have a deformation which goes to 0 with the number of sides. Okay, so I will give you a bit of history about near critical models. So again, it's the mathematical story, and there would be a lot to say about the physics story, but I don't know it, so I remain with the math. First, I told you about critical models. In 2 dimensions, there has been a lot of works coming from conjectures by physicists, works by physicists on the conformal invariance of those models, the fact that in the limit, those models become conformal invariant. Those models are also universal in the sense that they should not depend on the details on the lattice. And in the last 20 years, mathematicians have proved a lot of convergence and scaling limit results on the critical models. So in particular, some convergence results to SLE kappa. And so this is for the critical models. And if the weights are not critical, there's a completely different pictures where the models are ruled by large deviations and many different things happen. And in between the critical and the non-critical regime, there is actually this near critical regime where you scale the deformation with the mesh of the lattice, which has also been investigated for quite some time, and where you have in the limit a different picture from the critical model. So from the mathematical study started with a paper of Makarov and Smirnov, where they advocated that mathematicians should also study these models, which were already studied by physicists. And some mathematical work on near-critical models are the works on the near-critical Ising model by Duminil-Copin, Garban and Piet, by Park and by Chelka, Kisurov and Mahouf, who proved some convergence results for observables, some observables, and some convergence of correlations also. There was also a work which is important for us about the loopy rays random walk by Chelka Kenyon. So this is quite a recent history. And for the near-critical dimer model, the history started with the work of Sunil Shita, who was the first to study a near-critical dimer model on the square lattice with periodic weights. And he proved that the limit is non-Gaussian. So it is not the Gaussian free field, and it is also not a massive Gaussian free field, which one could expect. So he proved that this does not happen. Then the study was pursued by Nathanaël, Berestycki, and Levy, Onschmidt-Sivitz. And so they proved convergence of the near-critical dimer model and the associated tree model by temporalist bijection. But the limit is not explicit with their techniques, because what they do is they prove convergence of the tree model, and then convergence of the tree implies convergence of the height function, but towards something which we cannot describe. So this is not very satisfying, because we want to know what the limit is. So there was this work by Scott Mason about that, who proved that the 2-point correlation of the height function matches the sine-Gordon field. And later I extended the results of Nathanaël, Berestycki, and Levy, Schmidt-Sivitz to a much larger class of graphs. So I proved a kind of universality for this near-critical dimer model. And so this series of works led to the conjecture that the limiting height function is what we call the generalized sine-Gordon field with an electrical field, alpha. So I'm not so sure about the term, so maybe electrical field is not the best, but we didn't have a word for this, and we didn't see this object. This was a new object for us, so we named it. If you have better suggestions, I'm interested. And what is this object? The sine-Gordon field. It looks like the Gaussian free field, but there is this factor here, which changes the Gaussian free field, which is an exponential of something. The exponential of the field times the deformation vector.
What is a bracket?
This is the scalar product.
Is it obvious that this is a probability measure? Does the integral could be complex?
Yeah, not at all. I will come back to it much later in the talk, but indeed, this is not at all clear that this is well defined. Okay. And yes.
And what is that not?
Sorry?
Z not? What is Z not?
This?
Yeah.
This is a constant which needs to be identified. Yeah.
So coupling constant in field theory then?
I don't know. Yeah, I don't know. In our work, we can in our setting we can identify the constant, but in the conjecture they didn't know what the constant would be, so they put this. Maybe this is related to some conformal field theory stuff. I don't know.
I think it would be useful if you could just tell us, without nice scalar products and things, just on a square lattice or something like this, what would it mean for a diamond model to be slightly off critical?
Yeah,
So
sure.
just in terms of
Yeah.
black and white lotus.
Yeah, okay. Of course. So in the case where, say, alpha is constant, So this is the actually the usual case. Then you have a wide vertex. And here you have 1 plus 1 over plus alpha x over n. 1 minus n.
This is
Okay,
the,
and alpha is just alpha x, alpha y. Alpha x plus I alpha y.
sorry, this is the weight for the probability weight for it to be covered by a diamond.
To be what?
This is the probability weight for this edge to be covered by a diamond.
Yeah, exactly. So the critical weights are just 1, and here it's 1 plus some small constant divided by the number of sides. Yeah, by the mesh of the lattice.
Okay, so it sort of just favors one kind of sublattice or something.
Favors the
Not
line.
If alpha
Yeah.
x equal alpha y, what happens?
If alpha x equals alpha y, I don't know,
Yeah,
something
fine.
special. I'm not sure something special happens.
Okay.
Yeah.
Favor just that's what it's about.
Like it chooses a certain direction and then saying that every timer that starts from a y vertex would like to align in this direction.
Yes, yes, sort of, yes, yes. So for the associated tree model, it's the same. It favors the branches that goes in some directions. Yeah, something like this. Okay. Do you want more explanation, Jesper? No? Okay. Okay. Yeah, so there is a very nice heuristic for this conjecture coming from temporal bijection and imaginary geometry, but okay, I can explain it to you if you want, but I will not mention it now. Okay, so here is what we are capable of proving for this model. So we need some technical hypothesis. For example, the fact that V is log convex, so that's the fact that the mass I was showing you before is positive. We need that the domain has Temperlean boundary conditions, which I mentioned earlier. And we also need that the domain has a straight pattern like this. Actually, this is not very important in the end because we have some conformal invariance, conformal covariance results. But at least for this result, we need this. And what we prove is we give an asymptotic expression for the inverse Castellane matrix in terms of some operator, kappa, and the direction. So there's just some technical detail here, which is a bit annoying, which is that there are actually, I need to split the black sublattice into 2 sublattices, one with bullets and one with squares. And this is due to the choice of boundary conditions. But this is not so important for at least understand the statement. But what the statement says is that if I have a white point somewhere on the graph, and a black point somewhere else on the graph, I can compute the inverse Castellane. I can give you the asymptotic of the inverse Castellane matrix between, for example, this guy and this guy, as the sum operator between the 2 points, some continuous operator between the 2 points, and the direction of this edge. At the white points. So, okay, the important thing is that we have an asymptotic for the inverse Castellane matrix. And as I told you before, you can compute the height function from the inverse Castellane matrix. And in our case, well, we can do the same computations as in the critical dimer model. And we obtain that the moments of the height function are given by this formula, where the integrals are integrals along path also, like before. These things are signs, and we have integrals of some determinants of functions, which I will define on the next slide. But the important here is the structure. So you have some integral of some determinant of something. And okay. And okay, so the zi are the integration. And again, you have the path. You are computing the height function at many f1, f2, f3. The zi will be the displacement on the path.
What are the SI?
And the SI, that's a good question. So dzi to the 0 is just dzi, and dzi the 1 is dzi bar. Okay. So we have a formula like this, which is very similar to the formula in the critical case, but with the functions f and kappa, which are not the same. And okay, so in Kenyon's work, the thing is that the kappa, kappa star, and f, they are very explicit. They are defined in terms of the green function, so derivatives of the green function. And in our case, it's not so easy to, well, we cannot give an explicit expression for them. So actually, we define them as solutions of some boundary value problem. And to tell you what are how they are defined, I need to first tell you a bit about to introduce the notion of massive holomorphicity. So I say that a function f is massive holomorphic if it satisfies this thing. So the definition depends on the deformation vector alpha here. So it is really an alpha holomorphicity notion. And you notice that if alpha is 0, this is just a regular notion of holomorphic function. So this is an extension. And so what is kappa now? Kappa is a massive meromorphic function with a pole at W. So as a function of the second variable, it is just this massive meromorphic function with a pole at W and with given boundary conditions. Okay. So that's the function kappa. The function kappa star is defined similarly, but I didn't want to put the definition here. And for the f0 and f1 function, I need to introduce the massive Dirac operator, which is this thing here. So the Dirac operator would be the same thing, but with nothing on the diagonal. But now I am in a massive theory, so I put the alpha and alpha bar on the diagonal. And the f1, f0 and f1, they satisfy this thing. So up to the I vectors here, f1, this matrix is just an inverse of the massive Dirac operator, the f0 and f1, and with some strange boundary conditions coming from the Temperlian boundary conditions. Okay. Okay, so I told you what we obtain in the limit, which is
what is I2?
What is
you had an I2 on the.
Do you mean this thing?
No, on the right. Just on your boundary conditions on the Dirac operator.
Wait a second. That's the identity matrix. Yeah. Sorry. Thanks. And this is the tangent vector. the points Z. Okay. So yes. So I presented you the result, and now here are the objects appearing. So you see that there is a notion of massive holomorphicity and massive Dirac operator, which you may be more familiar with. And now what are some important features of this result? The first one is that I presented everything on the square lattice, but we can prove all this on a more general class of graph, which is the class of isorazor graphs, actually the double graph of isorazor graphs. That's the first point. The second point is that in our results, you can see that the limit is has some conformal covariance because it is expressed in terms of these boundary value problems. So if the problems were, if there's no deformation, the limit is expressed in terms of holomorphic functions, which are conformal invariants. But with this notion of massive holomorphicity, now you don't have conformal invariance in the limit, but conformal covariance. So if you move from a domain to another, then the deformation changes in an explicit way. So yes, so first the limit is conformally covariant. An important thing is that we deal with variable drift. So the deformation vector is a continuous function, but it changes over the domain, which to our knowledge was not done before, at least in the mathematical community. In near-critical models, people just considered the case of a constant deformation, constant vector alpha, so the thing that I pictured here. So the notion of massive holomorphicity, it was introduced in the constant case, but then in our case, since the drift is varies, the notion is more general, so we had to figure out what the good notion is. And an important fact also is that our proof does not rely on exact algebraic identities, because in the constant case, people use a lot the Bessel functions or exact identities with the weights, which we cannot do in the variable case, in the variable setting. So this is a new feature of our proof. And finally, a few words on the proof. The proof involves a full theory of discrete massive harmonic and discrete massive holomorphic functions. So I think many of you know the theory of holomorphic function and what tools you have to study holomorphic function in the continuum. And we had to develop so there is a similar theory for discrete harmonic and discrete holomorphic functions, which was very well developed by Chelkak and Smirnov. Well, it is a much older theory, but they gave a very nice toolbox on isorazor graphs. And what we do is we develop a similar toolbox for discrete massive holomorphic function and discrete massive harmonic functions. Okay, so I had some slides on the proof, but maybe I'll jump to the sine-Gordon field, and if I have time, I will come back to that. Do you have some questions so far? No. Okay. So I will skip the things that I am very familiar with, and I'll come to the things that I don't know very well. So yeah, I'm more an expert of the dimer model and the discrete stuff. And the sine-Gordon field stuff I had to learn a bit about, but I don't know so much yet. So you can ask a question, but I'm not sure I can answer everything. Okay, so I just recalled our main results, which is that the height function in the near-critical regime, it converges towards the field phi, which is defined by this. So it's just the same as before. It's the integral of a path of some determinant of some functions, which are basically the inverse of the massive Dirac operator with some boundary conditions. Okay, so I just rewrite it a bit more conveniently. Instead of writing the integrals, I just write the moments of the derivatives of the field, right? And here the SI is the same as before, D or D bar. It can be D or D bar. And so the moments of the derivatives of the field are given by the determinants of this inverse massive Dirac operator, right? And what was the conjecture saying? It said that the limiting field should be this sine-Gordon field. So far, those two things are very different. And I would like to tell you why those two things are actually the same and in which context. So the first thing that I would like to comment on is the definition of the sine-Gordon field, which is the question of someone in the audience. So the common sine-Gordon field, so if you forget about this variable deformation, if you take a constant drift vector, and so a constant mass, the common definition of the sine-Gordon field would be this thing here. So the scalar product in our expression, it becomes just a cosine of some beta, some parameter beta times the field. Okay, and the thing is, for beta smaller than 2, it is possible to make sense of this thing here by a regularization procedure. But it happens that for beta equals 2, which is actually our case, you cannot do that. So you cannot make sense of this integral as a function of the field psi. So you need to define the sine-Gordon field, you need to do a regularization, but at the level of this expression. Not just, you cannot make sense of this and then say that it has a Radon Nikodym derivative with the respect to the GFF given by this. You need to define it differently. So as I told you, well, unfortunately, or fortunately, I don't know, but our case is really this theta equals 2 case. So we need something different. And yeah, also for beta larger than 2, it becomes even worse. But we don't need that. We are at what we call the free fermion point, beta equals 2. So from the mathematical point of view, it was defined properly by Bauer, Schmidt, and Webb in a recent article of 5 years ago. It was defined in the case of the full plane. So the domain is just the full plane and with a constant drift vector alpha. And for bounded domains, which is what we want, it is actually a work in progress by two authors, Park and Webb, to just define the sine-Gordon field.
Just,
yeah.
In case you know, what did they do to define it?
Just
in words.
The Bauer, Schmidt, and Webb. It is a regularization procedure, but it is so that they have 3 regularization that goes to infinity at the same time. I cannot be much more precise than this for the moment. Okay.
So
yeah.
if it is not absolutely continuous with respect to Gaussian free field, why do we still call it sine-Gordon? Like so their work somehow extends this definition.
Yeah.
But it's not like adding a Radon Nikodym derivative to the Gaussian free field.
Yeah.
Why do we still call it sine-Gordon?
Why wouldn't we? Yeah.
Like it might have some similar features or something like that.
Okay, so you don't like the fact that this is called the sine-Gordon field. To me, this is the sine-Gordon field. So I don't understand what your question.
But like you mentioned that when data equals 2 or larger,
Yeah.
Like this field is no longer like cannot be constructed by some Rotten derivative.
Yeah.
But still it takes the name of the sine-Gordon field. So.
Yeah.
Maybe the question would be, what is the relation between the field that theta equals 2 and then the smaller than 2 already?
Well, except that they are defined by roughly informally by this expression, but that's all I can.
Okay, just that when we cross that critical point when beta equals 2, that formal description does not make sense.
Yeah, but you can make sets of this, but you need to work to define this. And for example, if you use the regularization procedure for beta smaller than 2, I guess you will have the same limit all along the value of the parameter b. Okay. Okay. So fortunately, these people will define soon. We are in touch with them, the sine-Gordon field in bounding domains, and we can rely on their work. Okay, but still, those two things are very different, and that's because at the free fermion point, so beta equals 2, there is the sine-Gordon model has a special property which is known as the Coleman correspondence, which is a kind of boson-fermion correspondence. Okay, what this Coleman correspondence says is that the moments of the derivative of the field, they are given by the determinant of something where this thing here are actually the inverse massive Dirac operator. So this is really what we want, right? Because we have in our result, we have the expectation, the moments of the height function in terms of the inverse massive Dirac operator. And this is actually something which is known for the sine-Gordon model, which has been known for a long time. And in the full plane, this is also proved by Bauer-Schmidt and Webb. And in bounded domain, well, this is also part of the work I was mentioning to you before. So Park and Webb, they are proving this identity for the sine-Gordon field in bounded domains. Okay, so this is why actually we really have proved convergence towards the sine-Gordon field. But we have proved convergence towards this fermionic form of the sine-Gordon field. Yes.
So your alpha is the mass of the fermion at the end of the day. This alpha deformation appears to be the mass of the Dirac operator. For a constant alpha.
In the constant case, yes. And in the general case, the mass, so I have some potential V. Alpha is the gradient of B, and the mass is the Laplacian of B plus the square root of.
Okay, thanks.
And if alpha is constant, this vanishes when m is the square root of the square norm of the deformation vector. Yes. Okay. And now I will conclude by so we have figured out these things, but I will just tell you what are the problems that still remain when we have done all this. Well, I could spend a lot of time on this, but I will just point the problems. So the first one is we have proved this moment. Well, we have an expression for the moments of the field, but does it really define something? Does it define a limiting object? Does it uniquely define a limiting object? So the first issue is to check that the boundary value problem I was mentioning has a unique solution. So the fact that massive Dirac operator can be inverted with these boundary conditions. So this is non-trivial for variable drift alpha and variable mass, or at least we didn't know any easy way to do it or any result. So if you know, please tell how to invert the massive Dirac operator when the deformation is varying. So that was the first problem. A second problem is that we don't know if this expression for the moment, it's uniquely characterizes the field. And this is a question that we had to solve, and we had to solve it using some Friedel determinant arguments. So here it's really the limit of my knowledge. We also have some we also have some issues with the domain because, as I told you, for our results, we need some domain which has a straight boundary here, and Park and Webb, this is us, and Park and Webb, they prove the result for the unit disk. So those two things are really not the same. Well, the unit disk doesn't have a straight portion, but we can figure this out because we have some conformal covariance argument to move from domain to another. So we are capable of saying that, our results also hold for the disk. And we also have an additional issue with the boundary conditions because our boundary conditions are inherited from the Temperleyan boundary conditions. And this is not the ones that are natural for Park and Webb because they are working with the Ising model. So we need to do some additional work, some gauge change to match their boundary conditions. And and that's all. So, thank you. Questions are also comments. If you have some interesting thing to say about this modified sine-Gordon, please.
You
speak.
briefly mentioned the imaginary geometry.
Yeah.
So you say it was heuristic?
Yeah.
In which sense? I mean,
Okay. Do you know temporal bijection?
I'm not using.
Okay. Do I have something to erase? Oh, yes.
The second building.
Oh. Okay.
But some was up too much. Just
Yeah, you know, but it's a very interesting question actually. So I'd like to say a few words about it, but I need to think a bit. So temporal bijection is bijection between you have some diagram configurations somewhere. Check it all and so the bijection is between the dimer configuration and a pair of spanning trees like this. And it is also related to the subject of the seminar. I'd like to say a few words about it. So you can, this is a bijection between dimers on the square lattice and spanning trees on the same lattice. All right. And okay. And the thing is, if you have height, okay, h is the height function at some place. Okay, h is the height function. Then the direction of the edge at the point here is given by exponential I times h in this bijection. So the height function, how the height varies, really tells you how the branches of the tree, where they go, the direction of the branches of the tree. And the thing is, in the near-critical regime, the probability of some phi function by Bernoulli's projection. It is the probability to see some tree. And for the tree, what is this near critical probability? It is the critical probability times the product of 1 plus e times deformation. So the weight of an edge is the critical weight of an edge plus some small deformation, which is the direction of the edge times the deformation. And then if you plug this thing here, inside this, and you use convergence of H towards the Gaussian free field, you really get the thing that get the conjecture. I could write it down. It's 5 lines, but I don't know if you're interested. You can ask
So
me.
it cannot be made rigorous? No?
Well, it cannot be made rigorous precisely because this thing is not well defined. And so we cannot say, okay, this thing converges towards the probability of the Gaussian free field, and this thing converges toward the radon-Nicotin derivative, because this thing doesn't converge to anything. So at least we don't know how to make it rigorous, and it looks pretty hard. So we tried a bit, but we didn't see anything, which is why we took this path.
Okay.
There was something special for that corresponds to kappa equal 2, right? In the SLE.
Mm-hmm.
So it corresponds to these parameters they had chi, the Miller-Sheffield work,
Yeah.
which is given in terms of kappa, right? So for kappa equal 2, what happened for chi?
I think it's square root 2 or 1 over square root 2.
Not exactly.
I think it's 1 over, I think.
Right.
Can I ask, is it quite nice that you introduce this parameter alpha, which is especially very mass? It would be nice to, in sine-Gordon, we have this extra parameter beta, and it would be nice to go below beta equals 2 because it's less trivial. Is there a conceivable way to generalize the dimer model with an additional parameter that has a chance of mapping to beta in the sine-Gordon side?
Oh, to a different beta, you mean?
Yeah.
So I know there's some work about interacting dimers with some interaction. I don't know if it could change the beta. That's possible. I will need to think about it, but it is possible.
You've been introducing repulsive or attractive interaction between two dimers.
Yeah. Yeah, I know there has been some work in this direction, and
For physicists, I think we know it changed.
you know it changed beta. Okay, yeah. So I guess,
But it's not in the whole point.
yeah. Well, there has been some works by mathematicians also, but I don't know what they prove. And yeah, I'm not sure we could do so much, but maybe we can do a bit. I don't know. I think my co-authors are working on or thinking about this kind of stuff.
Okay, more question? Okay, let's thank the speaker.